Okay, so welcome to this today's lecture. We will start recalling what we had done earlier. So we defined the notion of a basis of a vector space V in Rn and proved the following facts about the basis. B is a linearly independent set and generates V. That means every vector in V is a linear combination of elements of B, and it is a linearly independent set. Or equivalently, B is a maximal linearly independent set. So you can replace this condition that it spans by the maximal property, and it is equivalent to saying it is a linearly independent set such that LB of that is same as the earlier one, or it is a minimal set of generators. That is another property that we proved last time. We also said we will assume this theorem that any two bases of a vector space have the same number of elements. So that gave rise to the definition of dimension of a vector space. So dimension is the number of elements in any basis of a vector space. There can be different bases, but the number of elements in each base will be same for a given vector space. So that we called as the dimension. Some useful properties of independent and dependent sets. If a set is linearly independent, if a set S is linearly dependent and S is a subset of T, then the bigger set also is linearly dependent. Because what does independent mean? Here that there is a linear combination of elements of S which is 0, but not all coefficients are 0. But elements of S are also elements of T. So that means there is a linear combination of elements of T which is 0, but one of the coefficients is not 0. So T is also dependent. So if inside a given set you find a subset which is linearly dependent, then the bigger set itself is linearly dependent. And equivalent way of saying the same thing would be if T is linearly independent, the bigger set is linearly independent, then every subset also is linearly independent, because the property of independence is that if a linear combination is 0, all the scalars must be 0, right? If it is true for elements of T, then obviously it is true for elements of the subset also. Another way of saying a linear dependence is a set is linearly dependent if and only if, that is a definition actually of linear dependence. Or you can also write one element, at least one element of S is a linear combination of elements of the remaining one. And this is another property that we proved, namely if you have got m vectors in Rn, right, you have got m vectors in Rn and the number of vectors is bigger than the number of components, then that is always linearly dependent. So we observed that. Okay. So in R2 you have got 3 elements, 3 vectors, they have to be linearly dependent, right? They can't be independent. So that property we saw. Let us look at some vector spaces associated with a matrix. So let us take a matrix A, and these are the row vectors R1, R2 and Rm. There are m rows and each row is a vector of length n. Okay. So this is a m rows and n columns. Each row vector has got n components, right? So this is m cross n matrix. So these vectors Rm, R2, Rm, if you put them together in a set and generate a vector space, so that means the linear span of the row vectors R1, R2 and Rm is called the row space of the matrix A. So given a matrix, look at the row vectors, right? So look at the row vectors, there are m of them. So the subspace of Rn, each vector is of length components n. So if we generate a subspace, that will be subspace of Rn. So row vectors generate a subspace that is called the row space of. So that vector space has got a dimension, right? So that dimension is called the row rank of the matrix A. That is called the row rank of the matrix A. So what is the rank? Row rank, now we are defining a new term. Earlier we had the notion of rank. So what was the rank? In the row-echelon form, the number of non-zero rows, right? That was, now we are defining something new, but we will show it is actually equivalent to what the earlier definition is, that in terms of vector spaces, look at the row space, that is a space spanned by the row vectors, look at its dimension, and that dimension is called the row rank of the matrix. And similarly, we will have for the columns, so we'll take the matrix and write the column vectors C1, C2, Cn. So these are the column vectors, right? There are n of them, n column, m cross n matrix. So there are how many columns are there? N of them. Each column has got m entries, right? So this is you can write a matrix in the column form. So this we call the column form of a matrix. Matrix with the only columns are written down. So this is the column vectors. So look at the space spanned by the column vectors. Look at the space spanned by the column vectors. Each column vector is a vector in Rm, right? M components are there. So you will get a subset of subspace of, or you get a vector space which is inside Rm. So that is called the column space. So column space is a vector space in Rm, and the row space is a vector space in Rn. Okay. So these are the two subspaces, and they play some important role. We will see what are the role they play. But just one observation here: once we are written in the column form a matrix, if we take a linear combination of that equal to 0, these are column vectors, right, of the matrix A. If I take some linear combination and say it is 0, then that automatically implies that the A applied to the vector alpha 1 L2 alpha n is 0, right. This equation linear combination can be written as this, right, and that means what? That means that the vector alpha 1 alpha 2 alpha n is a solution of the homogeneous system, right. A applied to alpha 1 is 0. So that means this vector alpha 1 to alpha n belongs to the null space of A. Remember what was defined in null space? All vectors x say that Ax is equal to 0. So a linear combination of columns equal to 0 gives you a element in the null space. A observation which we will use it later on. So here is the first theorem about the row rank. Supposing A is a given matrix and you apply row operations to it, it will change to something. Rows will change. Now whatever the elementary row operations were, one was interchange of two rows, other one was adding one row to another, or multiplying a row by a non-zero scalar, right. Now if you take a linear combination of the rows and transform them by elementary row operations, what you will get? You will get some new rows, but they are linear combination of the earlier ones anyway. For example, if R1 and R2 are interchanged, you have not changed any linear combination, right. If you have taken R1 plus R2, you will get a new row, right. But in the new row, this new row is R1 plus R2, which is obtained from R1 and R2 itself by linear operation, right. So what we are saying is the row space of a matrix does not change if you apply elementary row operations to the matrix. You have got a you have got a matrix A with rows R1, R2, right? Rows, last row is Rm. Now if you apply row operations to this matrix, the rows will change, right? R1 tilde, R2 tilde and so on. But the row space of the transformed matrix is same as the row space of the earlier one. Row space does not change, rows have changed, because each row in the transformed matrix is a linear combination of the earlier rows. So it is not going to change in the vector space property, right. In a vector space, if you take two elements and take linear combination, that stays again in the vector space. So the basic fact is the row operations changes the rows, transforms the rows, but it does not change the row space of the matrix. So that is what, once the row space does not change, dimension will not change. So row rank of A is same as row rank of B if B is obtained from A by elementary row operations, right. Now This is just written there in the proof. Okay. So, as a corollary of this, you are given a matrix A and you have brought it to row echelon form. So, what is the rank of the row echelon form? Rank of the row form, that is a non-zero rows we defined earlier. And what will be the row rank of the row echelon form? That is same as the row rank of the matrix A. Let us try to observe that if you take the non-zero rows of the row echelon form, then that is a linearly independent set. The non-zero rows in the row echelon form is a linearly independent set, right. It is very easy to write that proof, but we will just skip the proof. We will look at examples and see how it works. Okay. So, this is the fact that if you take a matrix A, take its row echelon form, then you get non-zero rows, right. The row space of the two is same, row space of A is same as the row space of the row echelon form, and in the row echelon form the non-zero rows, the vectors, they are linearly independent. They are all linearly independent, and bottom rows are 0. Bottom rows are 0 in the row echelon form, only non-zero rows top, and we are saying they are linearly independent. So, what will be the dimension of, so these non-zero rows will form a basis for the row space of row echelon form, because they are linearly independent. These are the only rows which are available, which are independent. So, what is the row rank of the reduced row rank of the row echelon form? That is the number of non-zero rows, right, and that is what we have defined as the rank. So, what we are saying, the rank that we defined as the number of non-zero rows is same as the row rank of the matrix A, is same as the row rank of the row echelon form of the matrix. All three are same. So, let me repeat the reason again. Under row operations, the row space does not change, first fact. That means the row rank of A is same as the row rank of the row echelon form. Second fact, the non-zero rows in the row echelon form are linearly independent. And how many are they? They are precisely the rank, right. So, they form a basis, they are linearly independent and form a basis. So, that is the dimension. So, R, the rank of the matrix, is also the dimension of the row space. So, rank is equal to row rank is equal to row rank of A tilde, that is the row echelon form. All three are same quantities, right. There is a different way of looking at it, whether you just look at the number of non-zero rows or look them as a basis for the row space of the matrix A. Okay. So, this is one observation. Similarly, if we look at the column space, we want to claim that the column space of a matrix A is same as the column space of the row echelon form of the matrix. How is the, if you perform, that means if, how do you get the row echelon form? By applying row operations, right. And in terms of matrix multiplication, what is the row operation? Pre-multiplying it by an elementary matrix, and those are all invertible matrices, right. We observed that. So, we will use that fact now. So, if B is obtained from A by a row operation, then B must be equal to E times A, right. Now, look at the kth column of the both sides. The kth column of B is precisely the kth column of A pre-multiplied by E, that is a block matrix multiplication, right. So, if that is the case, okay, so what will happen? If the kth column of B is pre-multiplying by this, okay, then what we want to say is that in the, if there is a linear combination, rank does not, column rank does not change. Means what? If there is a linear combination which is independent in A and apply row operation, right, columns will change. We want to say that whichever columns were independent after row operations, they still remain independent. That will show that the column space of A is same as column space of the row echelon form. Is that observation okay for everybody? If some elements, some columns were independent in A, I apply the row operations, columns will change, right. But suppose I start with independent columns, I know that some columns are independent, right, and I transform them by the row operations, I will get some transformed columns. If I want to show that they also still remain independent, if we start with independent, they still remain independent, the transformed one also independent, I want to show that. So let us show that. So let us take a linear combination, okay, C1, C2, Ck, C1 of Bk1 and Cr of, so I am not taking all the columns, I am taking the k1th column, k2th column, and I have picked up some r columns, and I am taking a linear combination that is equal to 0 in B, okay, that is 0 in B. So what are Bk's? They are obtained from the corresponding column of A by pre-multiplication by the elementary matrix. So what is Bk? That we saw it here. The kth column is E times Ck. So put that value. So that means E times everything. So E is taken out, right? Distributive property of matrices. So this, but if this is equal to 0, what is E? E is an invertible matrix. E is an invertible matrix. So fact that every elementary matrix is invertible. So that means if E applied to a matrix is equal to 0, then that itself should be 0 because E is invertible. I can operate on both sides by E inverse if you like, okay. So that means the linear combination of C1, linear combination of these column vectors of A is equal to 0, right. So what we are saying, if a linear combination of column vectors in B is 0, then the corresponding linear combination in A is also 0, and if they were linearly independent, if these were independent in A, then what will that imply? That means all the scalars C1, C2, Cr must be 0. So what we have shown is if C1 Bk1 plus Cr Bkr is 0, then all are 0 provided the original ones were linearly independent, right. So this is a proof by saying that if you start with some collection of linearly independent columns of A and transform them by elementary row operations, the transformed corresponding columns are still linearly independent, they still remain linearly independent, right. So what does that mean? That means the column space of A is same as the column space of the transformed matrix, right. Independence is not going to change, right. So that precisely says that the column space of A is same as column space of B if it is obtained from A by elementary row operation. So if the space is same, dimension remains the same as for the row space we saw. So dimensions are same. So as a corollary, right, if B is the row echelon form, so if we take a matrix A, bring it to row echelon form, then the column space of A is same as column space of the row echelon form, and hence the dimensions are same, right, they do not change. And here is a theorem which based on these things only, what we have just now discussed. So it says if A is m cross n matrix, right, the row vectors of the matrix A tilde, that is a row echelon form, they form a basis, that is what we said earlier, right. If you take a matrix A, bring it to row echelon form, then the non-zero rows form a basis, right, that we said the rank is equal to the row rank, okay. So they form a basis. And similarly if I look at the pivotal columns of A, so what are the pivotal columns of A? You take the matrix A, bring it to row echelon form, you see where the pivots are coming, right. So mark down P1 the first pivotal column, P2 the second pivotal column. So look at the original columns, right, of the matrix, P1th column, P2th column and Prth column, then they are also, because independence is not going to change, right. So they are independent and span the column space. So that is the second observation, okay. They form a basis of the column space of A. So I am trying to tell you how to get a basis of the row space, how to get a basis of the column space. How do you get the basis of the row space? Take the matrix, bring it to row echelon form, the first, the non-zero rows, top on non-zero rows will give you a basis for the row space, right. The second one, the column space, take the matrix, bring it to again row echelon form, look at the pivotal columns now, look at the pivotal columns of A, original matrix, then they are going to give you a basis for the column space, right. And the third, the rank is same as rank of the column, so that we have already observed. The rank of the matrix is same as rank of the column space is same as the rank of the row space. One introduces that null space, remember, Ax is equal to 0, right, the all vectors x say that is called the null space. So dimension of the null space is called the nullity of the matrix A. So that is the dimension of the null space, okay. And there is a theorem which says that given a m cross n matrix, if you add up the rank of the matrix with the nullity and take the sum of these two, that is equal to n the number of columns of A. These two always add up and give you number of columns. Again, proof is easy, but some technical writing is involved, so we will not do that. We will use this result and verify in examples, right. So what we have said till now, let me just summarize before I start looking at examples. Given a matrix A, right, there are three important subspaces associated with it. One is the row space, that is a space spanned by the row vectors of the matrix. There is a column space spanned by the column vectors of the matrix, right. And what we are saying is the dimension of the row space is same as the dimension of the column space, is same as the rank that we defined earlier, the number of non-zero rows in the row echelon form of a matrix, right. So these are three important subspaces. How do you get their basis and dimension? So second step, the basis of the row echelon, the basis of the row space. What is row space? Is the row, vector space spanned by the rows. A basis is the non-zero rows in the row echelon form. They give you a basis, okay. And then once you have found a basis, you have found the dimension also, the number of that. For the column space, again look at the row echelon form, look at the pivotal columns, note down at what places the pivots are occurring, the corresponding columns of A you pick up, the corresponding columns of A you pick up, they give you a basis of the column space. So what will be the dimension of the column space? Number of pivots, and that is same as equal to the rank anyway. So column rank is same as the row rank, okay. But we also get a basis by picking up the corresponding column vectors, right. So these are the ways of getting the basis for them, okay.